Hi. Yeah, so I'm currently at Microsoft, but this work was done while I was at Princeton. And my colleagues on this one are Julian Cates-Harburg from Harvard and William Tang. So my talk today will consist of two parts. First, I will give you an overview of algorithms and hardware for training with reduced precision. And I will focus here on the FP16, or the half type, and the Volta GPU architecture. And in the second part, I will introduce the Fusion Recurrent Neural Net, which is a domain-specific deep learning framework integrating Keras and TensorFlow with a custom communication and global weight update implemented in CUDA-aware MPI. And I will use the real scientific data set to benchmark the FP16 training for this framework. Here in the table, you can see various popular convolutional neural network based architectures, as well as ones for based on LSTMs. Most of them were winners of the ImageNet contest on different year. As you can see from the second column, the number of layers has been getting increasing. The neural networks has been getting deeper and deeper. From the third column, you see that the number of trainable parameters has also been increasing, with an exception of, as we go from AlexNet to GoogleNet, the number of trainable parameters has dropped almost by order of magnitude. This is around the time when dropout regularization has been introduced. And in the last column, you can see the gigaflops. It's basically a measure of the compute necessary to train a neural network to full convergence. And that has increased by a factor of 20 since 2012 for convolutional neural networks. And if you pay attention to the last row, which shows the deep speech neural network, the compute required to train that is order of magnitude larger. That's why it's important to look at the smaller types, or types having less bits, to optimize memory network bandwidths as the neural networks getting deeper. Secondly, if we think about the faster training, which is also one of objectives, here we would like to use larger mini batch, and that's one of the topics I will discuss here as well. On the next slide, which is borrowed from Bill Daly's NIPS talk, I just show some of the popular floating point and integer types. Here on top is FP32, which is the standard type for deep learning, and FP16 and some integer types in the bottom. As you can see, basically the less bits we use to represent a floating or integer number, the less representable range we can cover, and the accuracy also decreases. And you can think of accuracy as the distance between two consecutive numbers, which can be represented by a given floating or integer type. The last line here is the fixed point. It's an integer 8 used to encode floating point numbers. Yeah, just like that. The problem with that is it's work for some tasks, but for deep learning, the scales of the weights, gradients, and activations are rather different, and they change as you go from layer to layer. So it's not enough to have just one fixed exponent. So to be able to use some floating point or integer type in training, it has to be first supported in hardware. So FP16 is supported in modern NVIDIA GPUs like Pascal and Volta architectures. It supports both math comparisons in the rounding to nearest even and arithmetics operations, and also modern Intel CPUs support typecasting to and from FP16, although they do not support the math. So we can use FP16 for deep learning applications. So what happens if we just go ahead and change, using our favorite deep learning framework, we just change the precision to float 16? Well, actually, a lot of things can go wrong. First, we can hit the overflow problem, which is quite rare, and it's manifested by the infinities and nuns in your gradients. Keras actually has a callback which would stop the training if you hit the none. And infinities can be avoided, for instance, by the gradient clipping. But once you don't take action, this is actually non-recoverable damage to the training. The second problem, which is a lot more often, is the vanishing gradient. It can happen in, for instance, simple recurrent neural networks. If you use like back props through time to train it and you unroll it over time, if the unrolling length is large, the gradients can vanish or explode. So the problem that I'm talking here is actually not related to that. It can happen in any neural networks simply because of the reduced representable range for a given floating point type. So it happens when we have small values for gradients, which is common, or the large ratio of weight to gradient, simply because of how the floating point arithmetic does. It shifts it aligns the exponents. And so from the next slide, for the next couple of slides, I will discuss the methods, or some of them are more like recipes to enable half precision and mixed precision training in your application. First, the mixed precision with master copy of weights. What it means is we are going to store the weights activations in FP16. And if our GPU supports FP16 math, we will do forward and backward prop also in FP16, but not the update. We will keep the extra copy of weights in FP32 and perform the update in FP32. The advantage is that it indeed solves the vanishing gradient problem, but it requires additional memory overhead, and typecasting can actually be slow. The second method, which I call mixed arithmetic precision, is essentially a variation of the first one, except we would use a dedicated hardware, Volta GPU, and the tensor cores. The tensor cores are essentially programmable matrix multiply accumulate units, which perform one matrix multiply accumulate operation per one GPU clock cycle, and there is 8. They perform this operation on small 4x4 matrices, which is essentially exactly what we need for matrix multiply and accumulate, exactly what we need for training the neural network. And there is 8 tensor cores per streaming multiprocessor in a Volta GPU, and you can run those in the parallel computational threads. So what one could do here is perform FP16, use FP16 for matrix multiply, but FP32 for accumulate. In principle, you can use either FP16 or FP32, but FP32 guarantees that there will be no loss, no vanishing gradients. So the next method is the loss scaling. It has a simple intuition, which I can explain using those two plots. What I show in the right plot is the weight distribution from the model that I've trained. What I did is I extracted the exponents for each floating point number, which is the weights, and then I histogrammed it and normalized to, well, 100%, plotting with the log y on the log in the y-axis. So as you can see, there is actually no problem for the weight distribution, and all of those are in the FP16 representable range for my model. As for the left plot, which shows the weight gradients, which are smaller numbers, you see that several bins are actually falling outside. For some of them, which are to the right of the red line, that would cause no damage to the training. In fact, there is several papers which show that larger gradients are more important for the training, and you can actually cut out some of the neighborhood of the 0, as those are not important for the final model convergence. And these are the ones that I cut out to the right of the red line are not important. However, what's to the left of the red line is important, and it would cause loss of accuracy. So what one can do is shift the weights and gradients to the right by several bins, and the number would be model specific to occupy the bins which are, well, currently not occupied. The way it's done is by applying a scalar factor to the loss before the back propagation. It's important to also unscale the weights before you applied it, before you perform the weight update. Otherwise, you would have to retune the hyperparameters to get the matching precision with the baseline model in single precision. A couple of more methods which are a little bit more convoluted, and one of them is actually applicable only for inference. First one is introduced by Song Han in the deep compression paper. What it does is it takes the weight matrix and it runs the k-means clustering on it, extracts the k cluster centroids, and introduces, instead of the large floating point matrix, introduces the integer matrix of indices that each weight of which centroid each weight belongs to, and thus saving space. Similar procedure can be done with the gradients, and one could think of the, well, quantized gradient, stochastic gradient descent. But I've seen the weight sharing used actively, but I haven't seen implementation of quantized gradient in deep learning frameworks available off the shelf. Finally is the dynamic fixed point representation, which actually is applicable only for inference. Here we would train the model in the full precision, full single precision. Then we would go layer by layer and extract some information, statistics about the layer, like minimum and maximum. And then we would use that information to decide on the number of bits in the exponent in the fixed point representation that I introduced in one of the first slides. Something like that has actually been used in Google TPUs in the integer 8 equivalent representation in the first versions of that. As you know, there is TPU v3, and they are doing something more advanced. So here the results, first of all, single GPU results, which were obtained on Volta using the mixed precision training and optionally adding the loss scaling, which were obtained in the ICLR paper by those authors, which are teams from Baidu and NVIDIA. As you can see from the top table, which shows the convolutional neural nets, simply using mixed precision training on Volta was sufficient and no loss scaling was required. For the bottom table, which shows some object detection neural networks, which are also based on convnets, one of them converged fine, and another one, which is multi-box SSD, actually diverged, and it requires loss scaling to recover the baseline accuracy. In the second part of the talk, I will basically introduce the Fusion recurrent neural net, the work that we did, and provide the benchmark results. But first of all, the hardware that was used for these tests, we were fortunate to have access to the Oak Ridge National Labs Leadership Computing Facility Summit supercomputer, which is to be ranked #1 supercomputer system worldwide this summer. It consists of 4,600 nodes, compute nodes, each of which having 2 IBM Power 9 processors and 6 Volta V100 accelerators, interconnected by NVLink within the node, and between the nodes it uses InfiniBand fabric. This is, it has a theoretical peak performance of 200 picoflops. The physics problem that we are trying to solve, I promise there will be not a lot of physics in this talk, is disruption forecasting in tokamak fusion plasmas. Fusion energy is a viable source of clean energy for the future, unlike fission, which is used in nuclear reactors and are not clean. In the laboratory condition on Earth, it can be produced in the tokamak-style devices, which tokamak is essentially a toroidal-shaped vacuum chamber surrounded by electromagnetic coil, which maintains the magnetic field, which confines the plasma and maintains the reaction. Plasma disruption are macroscopical instabilities which can stop the reaction, cause intense radiation and current wedge, and they can damage the device. The device that you can see at the bottom left is the ITER tokamak, which is currently being built on the southern France. And the device costs $25 billion. So it can only tolerate a handful of disruptions, and it would be costly that's why it's so important to have the software and methods in place to reliably predict and avoid the disruptions, at least 30 milliseconds before the event. Our group uses completely different fully data-driven approach to disruption forecasting in tokamak fusion plasmas, as opposed to first principle simulations and physics laws. The data we use is collected from the multimodal sensory diagnostics coming from the tokamaks. This includes scalar time series sampled with 10 milliseconds sampling rate, like plasma current, density, and radiated power. We also have one-dimensional time series, which means at every time step we'll have a vector, which is measured as a function of radius of the tokamak. What we do, and this is a general method which can be applied for other problems. How do we combine scalar and 1D data before feeding it to the neural network? Well, the solution for us was to use multi-input network. For instance, if you use Keras, you couldn't implement it with the sequential model and you would have to use functional API. We pass the 1D data through the sequence of convolutional and max pooling layers. Then we concatenate with the 1D data and then feed it to the sequence of stacked LSTM layers. So graphics are a little bit off on this computer, but this basically shows the full fusion recurrent neural net architecture. What I was just talking about is here at the bottom in red. We see 1D data goes through convolutional and pooling layers, then concatenated with 0D, and is fed to the series of stacked LSTM layers. After that, it's followed by the fully connected time-distributed layer, and we take the raw output of the neural network and we threshold it. If the raw output exceeds the threshold, we sound an alarm, and if it's below the threshold, no alarm, the shot is considered not disruptive. So it's essentially a binary classification problem. All of the parameters here in the neural network are determined via hyperparameter tuning. Among the prime challenges of training LSTMs on long sequences we need to be able to train the neural networks on the long sequences of variable lengths. Our approach uses stateful training with partial batch reset. So our data shown here in the cartoon on top, so the horizontal direction from left to right is time. And as you can see, the lengths of the shots vary by sometimes order of magnitude. So padding sequences to the max would not be an option for us. And other alternatives is bucketing, presorting it by length, and then bucketing wouldn't quite work because we have observed a strong correlation between the length of the shot and the disruptivity properties. So the shots that end with a disruption are generally shorter. So that wouldn't work for us. So first we use we compute gradients over a subsequent of time series. We save the internal states at the end of this iteration, and then for the next subsequence, we use those saved internal states as an initial state. That's essentially definition of stateful training in Keras, but additional improvement that we make is partial batch reset, which I explain on the next slide. So we maintain a two-dimensional buffer having m different plasma shots per batch, and those should be coming from different physical shots since we want to have it stateful. Then we feed t time steps at a time to the neural network. Then we shift the buffer to the right, to the left by t steps, and we check if any of the shots have ended. If the shot is ended, we fill the new shot at the particular batch index and reset the states for this shot only. That allows to train RNN to learn temporal patterns much longer than the unrolling length t, and potentially as long as the entire shot length. A few more words about the implementation of the FRNN, the framework that I have introduced, and here you can see the GitHub link to all of the source code. So it integrates Keras for layer definitions, TensorFlow optimizers. We also experimented with using session run TensorFlow runtime instead of the Keras feed or feed generator because it allows to have an access to the QDNN auto-tuner and basically select the like convolutional algorithms which are best for a given architecture. I don't know if you use familiar with the QDNN auto-tuner. And we use CUDA-aware MPI to implement distributed version communication as we do distributed training and the custom global weight update. So here's the distributed training flow for the FRNN. This is essentially the simplest version of what one can implement, a data parallel synchronous training. Starting from the bottom, we initialize network parameters randomly based on the model configuration. Then we distribute it among the n worker nodes on the cluster. Each of them has its individual model replica and performs the forward and backward pass. Then the local gradients are accumulated using the MPI all reduce, and the gradients are averaged. After that, we perform a global weight update and broadcast the global weight back to the workers. Simple as it is. Here is the results. So the first thing, if you want to validate whether our framework can support FP16 without reasonable loss of accuracy, we have to look at the, in this problem, since it's a binary classification problem, we looked at the AUCs. So these two plots on the left on the right show the area under the curve as a function of training iteration with the different values of the learning rate. And as you can see that the final numbers to which it converges are within the acceptable difference, although some differences during the turn-on region have been observed. I have later found that those could be also solved by using the warm-up period during training, which is not used in that paper on that slide. And the plot on the right, sorry, it's on the left. The plot on the left is the ROC curve on the test data set for FP16 and FP32 superimposed. As you can see, those are in a close agreement. Finally, this is one of my last slides, is the scaling properties. Since, we want to be able to train our neural network in a distributed way and on a cluster to take advantage of the hardware available for us. So here, formula on top shows the scaling model, which we write down on the piece of paper. So the time per epoch can be broken down into a pure compute time, which is constant, and the communication time, which is logarithmic, because we use MPI all reduce, which is a tree-like reduction. That's why log. There is a ring-like all reduce available out there in the Nickel 2 library from NVIDIA, which we haven't tried yet. So overall, normalized by the n mini-batch iterations per epoch, we get the O of log n by n. So on the left plot, you can see essentially that scaling model as a continuous black line, and the black polymarker dots is what we measured on that OLCF Titan supercomputer. And the plot on that was the plot on the right, and the plot on the left has two additional sets of polymarker dots, which are the measurements of the time per epoch obtained on the OLCF Summit supercomputer. Of course, not to full capacity, just to 200 GPUs at this time. And you can see that it gives significant improvement while maintaining the scaling. And the blue dots are the FP16 values, which is a half precision, so which gives additional 30–40% improvement. And yeah, that's all. I don't know how much time I have. I have 5 minutes. That's good. So as the neural networks models are getting larger, it's important to look into reduced floating point precision training approaches. That becomes crucial, and that gives us ability to optimize computational throughput and reduce memory and network bandwidths, allowing for faster training. We develop a domain-specific deep learning framework for fusion energy applications, which integrates Keras and TensorFlow with custom parameter averaging and global weight update implemented in CUDA-aware MPI. I gave out the GitHub link, which you can take a look. We evaluated this framework on a real scientific data set. So all of the tests you see typically are done on some ImageNet data set or a Pentry bank. And I think it's important to really look into like a real scientific data sets, like the plasma disruption data set that we did. And we got that with the loss scaling on Volta, we got comparable precisions and improved compute time per epoch. That is all, thank you. One last slide. So since I'm currently in Microsoft, quick note that our team is hiring. So if you're interested to work on some interesting deep learning problems at Microsoft, please come talk to me or send an email to Neil. That's all, thank you.
Thank you. Thank you, Alexey. We have time for a couple of questions. Anyone? Please use the microphone.
Hi, I have a question. So when you scale your model across so many nodes, more than 1,000, I wonder what is the batch size for your LSTM model?
Yeah, that's a really good question. So we can talk about the batch size on a single worker or the effective batch size, which would be the batch size on a single worker multiplied by the number of worker nodes. Right. So we experimented, if we use, for instance, a batch size of 32 on a single worker, for 1,000 nodes it would be 3,200. We observed that the performance start to degrade. If you don't do anything, performance start to degrade starting around 100 workers. So what one has to do, what one can do is you can use a dedicated learning rate schedule in addition to decaying the learning rate, you can also decay the base learning rate depending on the number of workers. I have something about that here. So that's what we did, and I have to tell, so we had good results up to 250, 300 workers, but for 6,000, that was a pure scaling test, and actually those models had performance penalty.
Okay.
But for a single node, we used from anywhere from 32 to 512 batch size, and that was determined in hyperparameter tuning.
Okay, thank you.
Hi, thanks for the talk. Can you run inference enough to actually act on the disruption and prevent it?
Sorry, can you repeat
Can you run inference fast enough to prevent a disruption? Or
yeah, that's a really good question. So the answer is yes, but there is still more work to do. So the minimum warning time is 30 milliseconds. If we can give a warning or a signal at least 30 milliseconds before the disruption happens, there is certain things we can do to shut down the reactor or take an action. The earlier you give a warning, the better, because we can actually, a person in the control room can shut it down and more things can be implemented. So moving the warning time farther away from disruption is one of the topics of research for this project. And the way this project will be evolving is perhaps we will go from prediction to control using reinforcement learning methods to basically for a neural network to like guide the machine to take action to avoid the disruption.
Thanks.
But yeah, that's a good question.
All right, anyone else? All right.
So I think in one of the slides you mentioned a challenge, the imbalanced time series. I didn't quite get how you address that.
Sorry, which slide was that?
This imbalanced time series data. As you said, the bucketing doesn't really address in that. So I didn't quite get your solution.
Imbalance? Different lengths. Yeah. Well, that's, yeah, our data has different lengths. So the way we collect the data, we have those runs at the tokamak, and we basically log different quantities like plasma current, plasma density, and radiated power with the certain time interval, like 10 milliseconds. And unfortunately, yeah, different runs have different lengths, and we cannot just cut it to be a certain length, because we would disregard important information which we could use to train a neural network. This problem is quite common. You know, like when you do text processing in NLP, sometimes you do zero padding, and sometimes you do pre-sorting by lengths and bucketing, so that you, within each bucket, you have approximately similar lengths, and you can pad it to the max without problem. Here, we implemented something different. We basically do stateful training. So we feed our time series in subsequences using smaller unrolling lengths to avoid like vanishing and exploding gradients. But we don't reset states, and we only reset state at the end of the shot. If you go to GitHub, there's actually a method which does that state reset. You can look at it. Maybe it will tell you more like than I'm telling you right now.
All right, thanks again. That's time.